This video demonstrates the use of the Xcode debugger on a C++ program. To use the debugger, we need to set a breakpoint. We set a breakpoint by clicking on a line number. The blue symbol indicates an enabled breakpoint. So if we start our program, it'll execute line 67 and then stop before executing line 68. and then we need to tell it what to do at that point. We can step into the program that's being called on line 68. We can just continue processing until something else stops processing. We can step over the call to main 2 on line 68, or we can step out of our current function, which is main. So let's set another breakpoint here on line 80 and continue to line 80. Now we can step over initialized list. Or we can step into initialized list. We can step into push front. We can step out of push front. Push front will complete, but we won't see it in the debugger. It'll just be in the background relative to us. We can step out of initialized list, and we're back to the call to initialized list. And we move on to the next line. This tool button here can deactivate all the breakpoints. So if we execute the program, it's as if there weren't any breakpoints. And it stops when it encounters a problem here. Turning on the breakpoints again. We can also make the breakpoint conditional. We bring up the context menu by control clicking or right clicking, select edit breakpoint, put a condition in here. Obviously that's false. So we won't stop at line 80. But we'll continue to line 82. So to review, this will deactivate all the breakpoints or reactivate them. This one continues execution from the breakpoint until something stops processing or until the code exits. This steps over the the call on the breakpoint line. For instance, in this case, we would step over print, just continue the next line, although print executes, as we can see here. Step into takes us into the program, into the function rather. Here we are in print. There we print 1, 2, and then we can leave if we want. 3 will go ahead and print, and we're back here, even though we didn't see the source code for the item 3 printing. So continuing, we get to our problem area. This area of the screen is our console output area. This is our debugger area. We can hide them both with this tool button at the top right. We can look at one or the other or both with these tool buttons at the bottom right. So we know that this text successfully printed. So to get an idea of where the problem occurs, we'll look for that text in our client program. And it's at line 354. So we'll set a breakpoint at line 355 and try and see where we get into trouble. There's a breakpoint navigator that you can access from this button. And it shows all the breakpoints that we've set in this project. We want to go straight to line 355 now, so we can use the navigator to disable all of them, or might as well just delete them. Go back to our project navigator. And here we saw that text is the last text in the console. We just executed line 354 where the text displayed. And now we want to see where we get into trouble. And it's there on line 361. So let's go into size. So size just spins through the linked list and counts the items. Number of items starts at 0, and for every item in the list, it increments number of items. There's 1, there's 2, and there's our problem. So curve pointer has this value hex 2 many zeros 1006 180A. The exception is a general protection fault, so this address is protected by the operating system. We shouldn't be trying to set it, but for some reason we are. This value came from the first next pointer in the calling object, which, if you recall, was list 1. Here's list 1 calling size. Notice that the first next pointer is hex 2 many zeros. Here's hex 2 many zeros. And now curve pointer has the hex 2 many zeros. So so it looks like this one got corrupted. It looks okay here, but then it doesn't after clear. So how did that happen? Well, let's watch clear execute. So it's like size. It just spins through the linked list, and for every item in the list, it frees the heap memory. So it says delete me to list. List points to 1. Then it moves list up to list next. So list is going to point to 2 now. There it's at 2. Then it's going to free delete me, which is pointing to 1. Now list is going to point to 3. And then it's going to free delete me, which is pointing to 2, and so on, until list is finally null, and it ends. So somehow doing that down here in list 2 messed up list 1. So let's put a breakpoint at the beginning of the function and see if we can find out where list 1 gets corrupted. Here are list 1 and list 2. Let's take a picture of them. Assign list 2 to list 1. It looks pretty good. List 1 still 1, 2, 3. Here's where it got corrupted. So somehow going through here and freeing these items messes up list 1. How could that be? The first, list is hex 1007 2B9EO, and by golly, list 1 list is the same value. So the problem is that list 1 and list 2 should be separate linked lists, but they're essentially the same because they point to the same elements, 9E0, 9D0, and 9C0, 9E0, 9D0, 9C0. So basically the problem is on the assignment. List 1 is, this execution list 1 list is 0D0, list 2 list is 590. Then after they execute, list 1 list is the same as list 2 because it's a shallow copy. If you haven't heard about shallow and deep copy yet, don't worry about it. You'll probably hear about it before too long. And it'll become clear at that time. What we need is an overload for the assignment operator. Which we happen to have, but it's commented out. So I'll uncomment it. I'll bring up the breakpoint navigator, delete all the breakpoints, and run the code. And it runs successfully to completion. Just to make sure you notice that, here's the button for the breakpoint navigator. There aren't any breakpoints now, but Now there are. And I can disable them. I can select them one by one or as a group. And now they're all gone. So I hope this demo was helpful. I hope you enjoyed it. And good luck with your coding. Thank you.